Hi everybody. Thank you for joining in on the call. I'm going to be talking about my project relating to anthropogenic roosting ability in bats and virus associations, which is actually two projects that I tried to shove into a 12-minute presentation. I'm Briana. I'm a PhD candidate at the University of Texas at Austin. And as Zoe mentioned, I did all of this work under the mentorship of Daniel Becker. I'm also co-advised by Lauren Myers and Nicole Gottinker at UT Austin. Always with the transitions on these. There we go. So in my title, I mentioned anthropogenic roosting. What do I mean by that? So the rapid conversion of natural habitat to built environments have varying influences on wildlife habitat use. Some wildlife have this ability to persist in these built environments by living in human-made structures or depending on them in varying amounts of frequency and duration. And bats specifically that roost in human-made structures are what I'm referring to as anthropogenic roosting bats. So bats that can be found in tunnels, barns, bridges, some of these examples and photos that you see on the slide. A big one being the Mexican free-tailed bat colony in the Austin Avenue Bridge. And so again, just anthropogenic roosting bats are bats that I consider having been found roosting in any of these structures that humans make. And so the determinants of this ability on a global scale is not well understood. And we want to know this information because we want to know what bats are living in these structures and what facilitates these usage or the usage of these structures, because these bats and these animals are at the forefront of the human wildlife interface. And so they may be faced with consequences of conflict from humans. And so these species may have unique conservation needs that depend on adequate management of conflict between humans and bats, like protection of certain buildings or bridges that humans may frequent, but may be restricting at certain times of the year for colony preservation of bats that really depend on those areas. Temples are a really good example of this. So knowing what characterizes that an anthropogenic roosting bat can help with anticipating future needs as well, as our environment continues to change and the built environment continues to expand. And so one source of conflict that is highly relevant for bats right now is the concern about pathogen spillover and spillback between humans and bats, just because they're living in close proximity. And so bats in this current time are threatened by retaliation relating to the perception of bats as being a nuisance or for hosting viruses. And we see in rodents that live in close contact with humans, they show higher probability of being a reservoir for zoonotic pathogens. This has not been studied extensively in bat species on a global scale. And so that kind of brings up the question, well, what about bats? And so to address one, what characterizes an anthropogenic roosting bat, and two, how this behavior influences viral association, specifically the importance of this behavior in predicting different viral outcomes. I've been working on two projects, the first being Cinerabat, the second being Bat House. So those are the repository names that we like to use one word for describing. So for project one, we looked at the determinants of anthropogenic roosting ability with the expectation that bats with this ability can be identified based on species traits and phylogenetic relationships. So I went and gathered and aggregated data on roosting ecology for several bat species, and I'll dig into that in the next slide. I also put together and grabbed some trait data information from these several well-known trait databases, and then used a machine learning approach to do a trait analysis And we also considered different phylogenetic analyses to think about phylogenetic patterns of this trait profile that describes anthropogenic roosting bats and their role in bat diversification. So the recipe for making a roosting data set is using a taxonomic backbone of extant species. So 1,279 that matched up well with the Virion database. And so I went through those 1,279 bats and categorized them as 0 for having evidence of exclusively natural roosting, and 1 for being recorded roosting in anthropogenic structures. And so again, that's, barns, bridges, buildings, roofs of houses, attics. Some I've seen water drainage pipes. That one was kind of interesting. And so I combed through all that literature that I could find online, historical records, several texts, and also when I could not find any roosting ecology, they were designated with an NA, and so that ended up being 237 bat species. And so we found that about 40% of bat species have been recorded roosting in anthropogenic structures. And so further descriptive analysis shows that roosting ecology data I was able to collect for all families by geographic realms and conservation status, but the distribution of roosting type varies wildly, shown with natural roosting here in purple, anthropogenic roosting in green, and unknown species in gray. You can see that it varies quite a bit, and a lot of these smaller bat families tend to have either only one type of roostings or roosting type or roost status. So based on variable importance provided by the boosted regression analysis, we were able to describe what makes an anthropogenic roosting bat. So to give you the top 9 traits that were kind of listed as high in importance here, anthropogenic bats are characterized by having a small geographic range, being a habitat generalist, being in areas that are relating to a lot of temperate zone distributions, like low precipitation, and low to moderate actual evapotranspiration rates and potential evapotranspiration rates. Being small in many ways, so having small litter sizes, having a small body in general, which I put in my notes, if I fits, I live, is how I describe that. And also low consumption of fruit and diet. So what you don't see on here is is also this association of higher percentage of invertebrates in their diet has been associated with anthropogenic roosting. So moving on to the phylogenetic aspect, are there clades more likely to have anthropogenic roosting bats? In summary, we actually found 2 clades that had significantly lower probability of anthropogenic roosting. And so those are pteropodid bats, Pteropodidae, and the superfamily Noctilianoidea. And both of those groups have many frugivorous bats or bat species. And so the next question was, do the phenotypes or this trait profile that represents anthropogenic roosting facilitate bat diversification? And one thing to note was that speciation rates were lower in anthropogenic roosting bats compared to natural roosting bats. So again, the opposite of what we were expecting to see. And so now that we define this trait profile of anthropogenic roosting bats, we looked at the role that anthropogenic roosting ability plays in shaping virus associations. So with the expectation that roosting would be an important driver of viral outcomes while taking into account several other factors, just because anthropogenic roosting kind of represents this direct pinch point of contact that could possibly facilitate pathogen transmission. And so we think that would influence these prediction of virus outcomes in some way. So we took the roosting data from before, also trait data, and then to calculate the different virus metrics or viral outcomes, we actually pulled those from the Virion database, and then applied also a machine learning approach to see how anthropogenic roosting predicts for viral outcomes. So richness, zoonotic proportion, virus host status, and zoonotic host status. So with the descriptive statistics, we see that viral associations and roosting status are distinct across bat families. Now you can see that. And so I have some boxes around some bats of note where you can really see that green blob really shifted over. So again, in fruit bats, so Pteropodidae, and two other smaller families of bats that have a lot of insectivorous bats. But these distinctions weren't heavily reflected in the proportion of zoonotic virus, just very slightly. And so getting to the importance of anthropogenic roosting ecology, it tended to vary by outcome. So as you can see in this plot where low value indicates a higher importance, out of 63 predictor traits, anthropogenic roosting was not really among the highest. So most of these across their respective models were pretty low in ranking, not being in the top 20 of most important predictors for virus richness, zoonotic proportion, virus host status, and zoonotic virus host status. But when you're comparing them themselves, it seems like the importance ranking is for anthropogenic roosting was higher for host status or virus host status. And so that's kind of reflected here in these partial dependence plots where the top two panels don't really show much of a difference in marginal effect on virus richness and zoonotic proportion, but you can kind of see a greater effect for virus host status in the green plot down on the bottom left. And you could see a slight but not super strong looking difference for a zoonotic host. And so quickly, does anthropogenic roosting improve model performance? Essentially, it does not. When I was excluding the anthropogenic roosting variable in these models predicting different virus outcomes, there didn't really seem to be a huge effect between including it or not. So to summarize really quickly, on a global scale, anthropogenic roosting can be identified by species characteristics, appears to have a moderate influence on being a virus host compared to other viral outcomes. And so as the built environment expands, it's important to identify which species live closely to humans to more directly implement measures to mitigate conflict relating to virus exposure risk, either through reducing retaliation due to fear of perceived transmission risk and reducing actual risk, which I imagine would also change, and we should watch as global change occurs. So a special thank you to Briana and Dan Becker and my co-advisors and lab mates for all of the support in working on these. So these are actually two of my dissertation chapters. So